All right, welcome to week number 4 of the Geography 473 673 Open Source Environmental Computing class. Last week for the assignment, we covered some time series data and specifically some wind data. We took a look at some wind data from January 2015 from one of our Newark stations. And so this is what the image should have looked like. Hopefully everybody had a good is pretty close to that. And just as a reminder, I'm really not a stickler on when it comes to grading, and I'm much more just focused on how far you're getting from, or how much you're getting from the course, and how far you're getting along with everything. So just try and get as close to this as possible. This week we're going to cover some oceanography with an example, and then have an assignment on global tree cover data. So before we get started on the actual tutorial, there is another essential function that we really want to cover here, and I'd referenced this and kind of used this last time, but we're going to get some practice with it and hopefully it'll make a little bit more sense. That function's paste 0. This function, along with its cousin paste and other cousin sprintf, what these functions enable you to do is combine a series of character strings or numbers in character strings or whatever you want into one long coherent character string. So for example, with this paste function, we're able to combine a collection of these character strings, file, number, and 32, all into one single phrase. The difference between paste and paste 0 is that paste 0 does not have any spaces. So 0 meaning 0 space, 0 separation of characters. For paste, it automatically adds in a space separation between the character strings, and then you can also add in a default separation argument that would put an underscore, for example, or whatever else you wanted. You could put 6 or exclamation point, or whatever character you wanted. Paste 0 we use typically just because most of the time we hopefully are not dealing with spaces or not a specific coherent underscore. Sometimes we do have that though. Sprintf can also do the same thing. It's a little bit, it's not quite as intuitive, I don't think, but basically the way that it's working is kind of in a similar way, and you are using kind of this %s. This is the same syntax that we referenced last time with the date time queries, but this has nothing to do with dates. So that's why I actually don't recommend using sprintf. This would be a more complicated example on how to use it, but that being said, I don't typically use sprintf. Some others do, I don't. So my favorite is paste 0. That's just what makes the most intuitive sense to me, and there's really not a whole lot of difference in speed. You're not really sacrificing a whole lot. But we can use a for loop here with a paste 0 that, for in this example, would be able to print out a number of file name paths and with the name extension. So this could be really useful if you need to read in a number of files. This is one way to go about doing that. So this is really helpful, this is really useful, and I encourage you to run through this on yourself, or for how these are working, how these different functions. Once you kind of run through this, it should be pretty self-explanatory. Try and debug and fix the following code here, and then print out path list and path list the first index. And what we want is for that first index of path list to look something like this. So try and get this, try and debug the code so you can actually get this. Next, whenever you're done with that, we're going to run through rasters. So we touched on rasters a little bit before, but really a raster is just a two-dimensional data set or a matrix of data that has specific geospatial coordinates. They can come in netcdf, geotiff, CSV, And typically for very large data sets, like remember when we dealt with the Go16 SST previously, how large that data set was. So that was over 5 million points. So 5 million different grid cells for that one file. And if you were to put that file stored in a CSV, it would be massive. So this is another example for why we use NetCDF and other formats. Maybe it might be a little bit more complicated like GeoTIFF, because they're a lot more efficient at storing data. We're also going to be playing with the Go16 satellite today. We're just going to be taking a look at a different sea surface temperature product, and this is the rolling 1 day. So this is a 24-hour rolling record of sea surface temperature over the Northwest Atlantic. So the first thing we're going to do here, we're going to load in our packages, and we have some new packages that we're going to be loading in, and I'm going to fire up RStudio here. And I'm going to put in a new R script, copy these over, and hopefully I can get rid of this warning right here. So hopefully that's not there. We'll see if it cooperates. So again, I'm going to run these library commands, and I have all of these packages already preloaded. And just another reminder, if you see a warning, most of the time you don't need to worry about it unless something really doesn't work downstream. But ignore warnings. The only thing that you need to stop and take a look at are errors. You might not have some of these installed yet, so you may have to go about and install packages, and you'll have to run through and maybe install SP or map tools or raster viz, etc. But to start with this example, we're going to start with a NetCDF file. The NetCDF file that we have is again in your datasets folder, and that is goes are rolling 1 day from August 14th, 2019. So for me, once again, this is in my datasets folder, which is in the Geog 473 folder, GitHub documents, and then all the way back to my root directory. Hopefully you'll be able to find your path by now. If not, go back to some of the previous videos for a little bit extra detail there. So we're going to load in our NetCDF file. So, and then we take a look at it, print it out, and we see a whole lot of metadata. So we have one variable, only one variable here, and that variable is SST. And then we have some dimensions. We have one time, and then a latitude and longitude. So we have a bounding box and one time, so it's just one snapshot in time of the sea surface temperature. In this case, that snapshot is the average of the last 24 hours. So it's a rolling average. And this has already been declouded. So we are only looking at sea surface temperatures when there are no clouds, or when that DQF, the data quality flag, was 0. But notice that because this is an average data set, we only have one variable, and that is sea surface temperature. After we have the file loaded in, we can run ncvar get and get the SST variable from the NC file. Run that, and let's take a look at what that looks like. Again, if we wanted to actually take a look at the summary of the data, because this is in a matrix form, we're going to need to turn it into a vector temporarily just for this line so that we can take a look. So we have minimum temperature of 5.3 Celsius, max of 34.9, and we have about 2 million NAs. So there's about 2 million points where, 2.5 million points where there are clouds in the way. Next, what we're going to do is we're going to read this matrix in, this SST goes matrix that we loaded in from the NetCDF file. We're going to read that in as a raster. We're going to convert that to a raster using the raster function. Notice that we loaded in the raster library, but the raster library has a raster function. So let's go ahead and run that line, and let's take a look at what SST rast looks like. Okay, so it's just, we have two dimensions here. It's, remember, longitude and latitude. We have 2778 by 1989. We have our resolution. We have our extents, which is wrong. We do not have extents from 0 to 1. It's really from 16 degrees north to 52 degrees north, and we'll fix that. Our CRS. CRS is a important thing, and what that is coordinate reference system. Whenever you get spatial data sets, because the Earth isn't flat, they come in wonky projections, and a lot of times the only projection that we can really get the best picture of, or the most common projection that you'll find data in is called it's just plate carry or lat long. So it's just a lat long projection because basically that is our way of distorting the shape of the Earth to make it flat. The reason that you see this a lot of the times is because you're looking at a two-dimensional computer screen, and this makes it a two-dimensional image. So our coordinate reference system is not defined right now, and we will need to do that. Now, real quick, on that note, if we actually take a look at the NC file and take a look at the metadata, you'll see that I added in here a note that says that this has been reprojected to EPSG 4326. EPSG is a code for the coordinate reference system. It's called an EPSG code. In this case, lat long is just the code 4326. So this will tell you sometimes in the metadata, not all the time, but a really good practice is to always reference your coordinate reference system so that it's easier for users downstream. So if you're ever making a data set, just do not neglect this. This is a very important thing because there's a whole lot of projections out there, and it really can distort your data and put it offline. So we need, if we take a look, go back to our SST RAS, let's take a look at that again. We're going to need to specify that, but we see that the values, we have a min and max. It just gives us a quick rundown of the values, and then we have the shape and size. So what we really want to do is we want to take a look at this. So we're going to use the image command from the raster package. Say image of SST rast. And boom. Remember how long level plot took to plot 5 million points? This just happened in maybe a 2/10 of a second. And so this is our sea surface temperature data. Now, we notice another thing. This is flipped incorrectly. So here's Florida. Here's Mexico and the Yucatan Peninsula. Here's the eastern seaboard. Here's Newark. So this is flipped incorrectly. So we're going to need to edit that. So one way that we can do that is, first, what we can do is we can transpose the data. So when we transpose it, basically what we're doing is, if you imagine this data to just be like a blanket, and just imagine it as a blanket with the top side is blue and the bottom side is white. What we're doing is we're grabbing the top left corner of that blanket with the blue side up, and we're pulling it down to the bottom right and flipping that blanket over by the corners. When we transpose it that way, now what we're going to see is that the white side is now up, so we've flipped it corner to corner, and typically that's done top left corner to bottom right corner. That's what's going on there. So if we actually go ahead and we run these lines, we're gonna reclassify SST RAS as the transposition of the SST RAS. Now we rerun. Okay, we're a little bit closer now. Now we're just kind of upside down, and a big reason for that is because we grabbed it corner to corner. So now what we need to do here is, this is clearly just upside down. What we need to do is flip it. So there's a handy flip function associated with the raster package. And the flip function, we run a help on that. We have an x, which is a raster object, and a direction, which is either x or y or 1 or 2, and 2 is equal to y. I just used 2 for that, and so we're going to reclassify now SST rast, which remember is our transpositioned SST rast, to a flipped SST rast. So let's run that, and let's run an image on SST rast, and finally we are right side up. So now this makes sense. We're over here, here's Florida, here's Mexico, the Yucatan Peninsula, Great Lakes, and Newark is somewhere up here. So That's all looking good, but what's not looking good? Let's print out SST-rast again. The extents are way wrong. The extents are not 0 to 1 and 0 to 1. We need to classify those extents, and we need to manually put those in. And then again, the CRS is undefined. So by flipping and basically putting this data right side up, we were not able to get where we needed to with the metadata. And this metadata is absolutely crucial for a raster. So what we're going to do now is we need to grab our latitude and longitudes from the original netcdf file. And again, these are just going to be some vectors with some latitude values and some longitude values, and basically just the row and column values of these grid cells, if you imagine it like that. The extents are going to be the extent of the SST-rast we can classify using the extent function of SST-rast. So we're saying, hey, the extent of SST-rast is going to be equal to this. And the extent is just equal to the minimum ln, the max ln, the min lat, and the max lat. And so if we look at this and we take it and we think about it like this, we have our xmin, xmax, ymin, ymax. Xmin, Xmax, Ymin, Ymax. And so we're just going to grab that minimum longitude value, which is negative 99.99, the max longitude value, negative 50, the min latitude value, 16, and max latitude value, 51.98. So I'm going to run this line, and now let's print out SST-rast again. Now our extent looks exactly like it should. We have an x minimum of negative 99, x maximum of negative 50 degrees longitude, min and max 16 and 52 respectively. So now let's run an image on SST-rast. And look, same exact image, but now we have the right coordinate systems at our edges here. So now this is looking a lot more like a map. The only other thing we really need to do, and this is more so just good practice, is to specify the coordinate reference system. In this specific case, this plot will still look exactly as it should because it is automatically assuming that we are in a lat-lon projection, because the coordinate reference system, that is just the most widely used, so it's automatically assuming that even though it's not specified. But let's specify it for good practice. So just as we had with the extent above, we're going to classify the CRS of SST-rast equal to this coordinate reference projection string. So this, you can find these strings online. There's a whole entire catalog of EPSGs, spatialreference.org, and you can run through all of these. You can run through epsg.org. And you can run through the codes, and there's so many. So what we want to do here is we grabbed this code, and the only reason that I know what this code is I can type in just into Google EPSG 4326 projection string. And we click on the first one, and sure enough, the WGS 84. That's exactly what we're looking for. And what this is technically called, you'll see in a lot of these kind of websites, is proj4. It's a proj4 string. It's all of a sudden this pops up super small, but we have the projection, which is lat-lon, the datum, which is where the reference point is for the prime meridian. We have and plus no defs. I don't actually know what that means. I'm sure that there's a description of it. Sometimes they have those decided. And then our ellipsoid, this parameter, which is WGS84. So we're just going to run that, set the CRS, let's print out SST-rast again, and now we have a nice coordinate reference system right there. And now we can run SST-rast, and again, whenever we use this image functions, unless CRS is defined as something other than this, it's going to assume that it is in this long lat-long projection. So that's all good. We did that and it looked great, and we can also use a level plot instead of our quick handy dandy image function. And this level plot goes a lot faster. And the reason being is because we actually converted this to a raster. So raster is just a very efficient way to store your data in R. So notice how we have a large raster layer versus a large matrix. If we were to actually go ahead and plot SST goes instead of SST rast, even though they're the same size, R would take a lot longer to plot the matrix, as we saw the other day. But this is nice. It gives us another nice picture, and with some details about the sparsity or prevalence of data. So where you have thicker bars down here, there's more data, and where you have thinner bars like up top, you notice that along this line of latitude, there's really not a whole lot of data. So that's what level plot can do for you. And then the other thing that we can do is we can add in layers to our level plot, such as land layers. And what we're going to do for this specific example is we're going to use our getData function. And getData is a function from the raster package, and all it does is grab geographic data, and it will download this data, this shape file and these state files behind the scenes. So what that means is whenever you have all of these packages downloaded from R, they're stored behind the scenes. You can find them on your computer, but it might be kind of tough. They're not stored in like your documents folder or your downloads or anything like that. It's stored in behind the scenes so that it's actually to prevent really the user from touching the files and messing with them. These files are designed to not be messed with. They're just supposed to be downloaded in a plug and play, and they're also there so that you don't accidentally delete them. So you can find these. They're on your computer, and they get stored there. And the exact same happens here with this getData function. And what we're doing with this getData function is we are downloading the GADM dataset, and GADM is country, and in this case, we want from this dataset. This is a larger dataset of countries. We want the USA country, and we want level 1 data. So I encourage you to read through these. It just kind of gathers this shape file, and what it's doing is, where it's just downloading this specific type of shape file for you. So let's go ahead and run that command. And USA, now this is read in as a spatial polygons data frame. So this is a special type of data frame where we have polygons in it, just the shape of the United States. Then we will do a level plot using our SST rast, and we'll get rid of that margin. We don't want it. We'll add in par settings, so we'll add in a color theme, and then we'll set our title using the main argument. We're going to store this as PLT. So notice what happens here. I run this line, no plot happens. That's because I stored it as PLT. So I stored it as an object that I haven't called on that object. So I need to print that object out in order for this to pop up. And let's say I want to print it out, but then I also want to add this layer of spatial point. We loaded in this package up here. We haven't talked about it too much, but SP is spatial point polygons. And we want to use our USA spatial polygons data frame, which we just loaded up here. Color to be black, the fill to be gray, and the line width to be 0.14. So let's go ahead, run that line, and might take a couple seconds here. We're still running, and that's because the shape file is pretty big. It's 48 megs. It's not bad for a shape file, something you're just holding in internal memory. And we finished running here. We have the sideways caret, the blinking cursor, so it just might take a couple seconds for this to pop up. There we go. So you can actually go ahead and you can add Mexico and Cuba and all these other countries, and there are other ways you can add in these land files as well. And we'll actually touch on that in much greater detail in the advanced R section of this course, which happens in the spring. But this is just a quick example right now of how you would go about adding states to that. So that is how we go about doing that. We did that the hard way. What I mean by that is we read open this netcdf file first, then we did an ncvar get, on the file, just like we normally would opening up any netcdf file, and then we converted it to raster. The easy way to do this is just to open netcdf file directly to raster. So raster actually has this capability where if the netcdf file has the right metadata and the right attributes to the file, you can load this file, this netcdf file, directly to raster. So I just opened this up, and now look what happens. We just opened that. When we opened this up from scratch before, and when we print out just from scratch, remember SST Rast has poor extents, doesn't have the right CRS, and everything's flipped upside down and inside out. Upside down, inside out. If we load it directly to a raster, so this is our netcdf file right here. We load it directly to raster because this specific netcdf file is stored correctly, has the right metadata, the right attributes data in it. Now, if we run an image on, if we print out SST Rast, look at that. Automatically loaded in are the CRS and the extents. And then, when we plot it, it's already in its exact correct spatial orientation. Here's Florida, here's the Yucatan Peninsula in Mexico, Eastern Seaboard, Newark. So this is the shortcut, and the reason that we went the hard way first is because sometimes netcdf files are not created properly, and they don't have the proper metadata to make this raster function behave correctly. In this case, you can use that. As I said before, you can also use this raster for TIFF files. And GeoTIFF is just a type of format, and it's also an efficient format, and a lot of you will see GeoTIFFs if you work in the geography department as a familiar file storage convention. So the other thing we have here is we can load this. We're going to play with this TIFF file right now that's also in your datasets folder, and your TIFF file is called goes SST TIFF. And we can also load this TIFF file directly to raster. And so let's go ahead and do that. So now we print out the Rast, and same thing. CRS is already loaded in there. The extent's already loaded in there. And we have a new name, and that name is goes SST. And now if we run an image on SST Rast, we just ran. We have sideways caret and blinking cursor. It's the same exact image as before. So this is the advantage of GeoTIFFs and netcdfs. They're just super efficient functions and really just allow you to take, huge quantities of data and process them and image them, plot them up. This time, for this next example, what we are going to use instead of the get data function from raster is we're going to plot the same exact thing using this world simple dataset. This is an automatic base dataset R already has. So let's throw this down here and watch what happens. I'm gonna open data on world simple, and boom, right pops up here, world simple spatial polygons data frame. Notice that it's significantly smaller, and this is for the entire world, not just USA. So this is just a different way to grab land data or land mass data or coastline data, whatever you want. And without much effort. We just downloaded this. R already had this installed for us. So let's go ahead and run that, plot it up, and you'll see in a second here, there's the coastline. It's really ugly, it's jagged, and it just has these country boundaries and a really ugly coastline. It's nice because it allows us to get a quick idea. Okay, yeah, this is all spatially oriented correctly. If you had a wonky projection, if you had an incorrect projection declared, and there was a mismatch of projections between World Simple and SST Rast, you would have ocean color or ocean temperature over top of this landmass data. That's not what we want. The reason that this works and behaves is because in both of our examples, in up here line 31 USA and down here in World Simple, the default projection is lat long, which is exactly the projection that all of our data has been in thus far. The last way I'm going to show you to go about loading in a data set would be to actually have shape files stored for you already. So in this, you can load your own shapefile. And in this case, what we're going to be using is the world.shapefile that is in the datasets folder and the world shapefiles subfolder. So this is a really important thing here that I want to talk about. Shape files are incredibly useful and important. They contain polygons of state boundaries, country boundaries, water masks, land masks, etc. Within this world shapefiles subfolder, and I'll just go to this real quick so you have an idea. You have three files. You have a shape file, you have a DBF file, and an SHX file. Even though we are only loading in this shape file, even though we're using this read OGR from the RGDAL library, we're only using that to load in this one file. Behind the scenes, this function is going to be taking a look at the SHX and the DBF. These particular files hold extra metadata information that the shapefile doesn't hold. So all of these three data sets, these three files, need to be within the same folder. And even though we're only loading one, it's opening up SHX and DBF behind the scenes. Now that that's already loaded in, we'll take a look at this over here. There's world.shape. It's up there in our data environment, and now we're going to throw that in here just like we did with the others. And it's another thing, it's important to remember that this is also automatically in the lat long projection. We're going to copy all of this over, and we're also going to use, so far we've only been using the spatial shape files from R packages or that are already pre-installed with R. This time, since we're using our own data set that we have downloaded ourselves, let's also go ahead and throw in our own map theme. So we're going to throw in our own raster theme, our own color scheme here using brewer.pal. And this comes from the R Color Brewer library. So what we're doing here is we're making our own palette of colors, and we're throwing 8 different reds, 8 different shades of reds in here. So now we go through map theme, and it's a lot of ugliness, but let's see what happens when we actually set that map theme as our par.settings. Let's go back over here, and boom. We have these different shades of red. We have our coastline, which is a lot nicer. And let's go ahead and let's make this color black. And let's make the line width LWD 0.8. And let's see how that works. That's a little bit better, but what we can see here is that we have a much more defined coastline. The Delaware Bay looks a lot more realistic. It even captures some of the river as it goes up through Philadelphia. And we also have a much more defined Chesapeake Bay right here, and just a much nicer image as a whole. Also, we have a lot nicer of a color bar right down here because this is from August 14th, and water's hot here. It's not exactly great to have blue coloring on days where it's, times of year when it's this hot. So this is how you would go about doing that. And if you want to set a different color up here, we can just run a question mark on brewer.pal. And we see that brewer.pal makes color palettes from the color brewer that are available as R palettes. And we get an idea about the colors that we can select right down here. Sequential palette names are blues, BUGN for blue-green, BUPU for blue-purple. We have greens, and then down here we have reds. So if we wanted to, for example, change this to blues, let's say that this is, we for whatever reason want this to be blue data. All we do is we plug blues in here, and we'll get a color palette full of blues. And we saw that for a second, and now I don't know if it's going to cooperate. Let's try again. There we go. Okay, so we have blues in here right now. And then there we go. Now we have our color bar, our coastline from the world.shape, etc. So that's how you go about handling raster data. So in this, remember, we started out the hard way where we just read in the netcdf file directly to a netcdf variable and then as a raster, and then converted it to a raster, and we had to flip it and transpose it to make it upright, and then we had to declare our own extents and coordinate reference system. Sometimes you have to do that if the netcdf file is not stored in a proper format. We use level plot and we added in some country boundaries here. Then we decided to read in a different file as a TIFF file, and we read that in straight to raster. And also, along the same example, we also read in our initial netcdf file straight to raster as well. And we noticed that because that netcdf file is stored properly, we were able to get around the headache of flipping, transposing, setting all that, because the netcdf file is stored correctly. All of that data was read into raster correctly as well. Then we use the world simple library, which is a default coastline library from R. And then we read in our own file that you have stored in your datasets folder right here. And we did that from the rgdal library using the read OGR function. Ignore this warning. I could not get rid of this. I have no idea why the warning had to keep popping up. But anyway, for this assignment, what you're going to do is we're going to deal with a tree cover dataset, and that dataset is treecove.nc in your datasets folder. We're going to open the tree cover data and we are going to read it as a variable with tree cover percentage as a variable, and we're going to remove bad values. And what that means is you'll see values, run a summary on the data, you'll see values outside of 0 and 100, and we know that you can't have below 0% tree cover. We're going to plot tree cover variable using a green theme. Be sure to add coastlines via any of these methods up above, and ensure that the correct latitude longitudes are displayed. Add a title, and throw that resulting image to the Canvas assignment 4. So this is what we're looking for right here. So you see that the Brazil, it's this tropical area of Brazil, we have a ton of tree cover. Tropical area of Africa, we have a ton of tree cover in Indonesia, and then we also see we have these boreal forests up here, and that looks good. This is exactly what we wanted to check out with this tree cover data. Cool. All right, well that concludes this lecture for week number 4.